This video is about the amazing mid-latitude Gulf Stream. The Gulf Stream is one of the strongest western boundary currents in the western North Atlantic. Its velocity reaches up to 2 meters per second with a transport volume of approximately 150 sphere drops. This raises three important questions. How did the Gulf Stream form? Why is it confined to the western boundary? Why is the Gulf Stream so powerful? Through this video, we will explore the answers to these questions. To understand the Gulf Stream, we first need to examine how gyres are formed, starting with wind stress. Wind stress exerts force on the ocean surface through friction, causing horizontal water movement. If the Earth didn't rotate, water would simply oscillate between the low-pressure zone at the equator and the high-pressure zones at the poles. However, due to the Earth's rotation, air moving from the equator toward the poles is deflected eastward. From the poles back to the equator is deflected westward. In the southern hemisphere, these deflections are mirrored. This leads to the Ekman transport, where surface water moves to the right of the wind direction in the northern hemisphere. This causes surface water convergence in the center of atmospheric anticyclones, leading to water piling up. The sea surface height rises toward the center and isotechnic surface flow. A surface pressure gradient forms directly toward the center. At this point, geostrophic circulation occurs, balancing the pressure gradient flows with the Coriolis flows. In the northern hemisphere, this results in an anticyclonic flow. In the southern hemisphere, gyres rotate cyclonic. Thus, large gyres are established in both hemispheres. The Gulf Stream exhibits a striking asymmetry, and this can be explained by two key factors. Firstly, variation of the Coriolis parameter. According to the geostrophic flow equation, if the pressure gradient remains constant, an increase in Coriolis parameter causes a decrease in velocity. So F2 is bigger than F1, U2 is smaller than U1. This means the Coriolis force increases with latitude, leading to a reduction in flow velocity at higher latitudes. This variation results in stronger western boundary currents and weaker eastern boundary currents. Secondly, influence of ocean boundaries. Western boundaries such as the eastern coast of the United States play a critical role in shaping the Gulf Stream. Friction with the coast increases flow shear, generating positive vorticity. This intensifies the flow, making it faster and narrower along the western boundary. Now let us explore the key vorticity concepts that explain the Gulf Stream's dynamics. Planetary vorticity is everything on Earth, including ocean, the atmosphere, and balls of water, rotate with the Earth. Relative vorticity is the rotation rate of the ocean and atmosphere is different from Earth's rotation rate. Absolute vorticity is the sum of the planetary vorticity and relative vorticity. Potential vorticity is the rotation rate of a column of flood changes as the column is expanded or contracted. For the key dynamics of potential vorticity conservation, when a flood column moves and its height changes, its relative vorticity must adjust to conserve potential vorticity. For example, if the column becomes thinner due to the topography, its local rotation intensifies. Similarly, when moving from a higher latitude to a lower latitude, the decrease in Coriolis parameter requires an increase in relative vorticity to maintain conservation. At the western boundary of the Gulf Stream, strong velocity gradients further increase relative vorticity, intensify the flow. In summary, the Gulf Stream forms through the combined effects of wind stress, Ekman transport, Coriolis acceleration, and geostrophic balance. Its asymmetry arises from the variation in the Coriolis parameter and the influence of ocean boundaries. Changes in column height lead to adjustments in relative vorticity. Changes in latitude cause variations in the Coriolis parameter, which also require adjustments in relative vorticity. Gulf Stream plays a crucial role in both the global climate system and marine ecosystems. These are the references. Thank you so much for listening.